mynews.studio.
A teenager walks out of the hospital cancer-free after gene-edited cells save her life. Is this a sign that a cure is here? Or could it just be the beginning of a much longer process?
Today is 2025-12-13. This week, researchers in London announced that BCAR7, a gene therapy using engineered white blood cells, has helped 7 out of 11 patients with previously untreatable T-cell leukemia reach long-term remission. That includes Alyssa Tapley, who was the first to get the treatment and is still cancer-free at age 13. But what exactly is BCAR7, and why does this matter so much?
BCAR7 is a type of CAR T-cell therapy, but instead of using a patient's own T-cells, doctors use donor T-cells. They edit these donor cells with base editing to remove specific genes, then program them to attack the cancer. The big difference here is that for T-cell leukemia, older therapies often failed because both the cancer and the therapy target the same kind of cell. BCAR7's edits allow the donor cells to survive and do their job. The outcome? Out of 11 patients, including 9 children, 7 are in complete remission after 3 years. For a group with very few options, that stands out.
But only 11 patients so far. Isn't that a pretty small number? What do scientists actually need before this could be considered for wider use?
You're right, the group is small. Early phase trials like this are about possibility, not yet about typical results. To go further, researchers will need much larger studies, ideally across several countries. They'll want to see that remissions last, look out for any serious late effects, and confirm that it works beyond just one hospital. Relapses are a concern too, especially if leukemia cells lose the CD7 marker that BCAR7 targets. And then there's the practical question: can these donor-derived, highly edited cells be made reliably and at scale?
Manufacturing sounds like a big challenge. What's actually involved in making BCAR7? Could it ever be produced outside top-tier centers?
It's definitely complex. You have to edit several genes in donor T cells, use viral vectors, and maintain tight controls to prevent contamination or unwanted changes. That means specialized labs, GMP cell processing facilities, cold chain logistics, and trained teams. In theory, because BCAR7 uses off-the-shelf donor cells, scaling up should be easier than with personalized CAR T therapies that are custom-made for each patient. But realistically, for now, it's going to stay in advanced centers.
And what about risks? Gene editing always raises questions, like off-target changes or immune complications. How does BCAR7 compare on safety?
So far, the main side effects look similar to other CAR T therapies: low blood counts, cytokine release syndrome, infection risk. These are expected and usually manageable, especially in experienced hospitals. One thing to note is that BCAR7 uses base editing, which avoids making double-strand breaks in DNA. That could mean less risk of chromosomal damage compared to older methods like classic CRISPR or lentiviral CAR T approaches. Still, we'll need a lot more data over the long term to be confident.
Let's look at the ethics for a moment. Editing immune cells in children, especially when they have no other options. How do families and researchers handle the uncertainty?
It's one of the toughest questions. These are somatic edits, not ones passed to future generations, but the tools are powerful. Families in urgent situations may feel pressured to try whatever's available. So informed consent is really important, making sure everyone understands the risks. There's also a fairness issue. If only a few can access this kind of therapy, it could increase health inequalities.
Which leads to access. If BCAR7 proves effective, how do we avoid it being limited to wealthier countries or major cities?
There are 3 main steps. First, set up regional hubs for manufacturing and training so more places can make and give these cell therapies, not just London or New York. Second, work out approval and pricing systems maybe tying payment to actual patient outcomes, like only paying if someone stays in remission. Third, improve diagnosis and referral networks so people get identified and treated in time. And it's crucial to involve communities in decisions and communication to avoid making disparities worse.
Compared to other gene or cell therapies, does BE-CAR7 offer any clear edge, either in how well it works or how easily it could be scaled up?
The early numbers are promising. About 82% of BE-CAR7 patients went into deep remission, and 64% are disease-free at 3 years. That's striking for such hard-to-treat cancers. Scalability could be a real benefit since it's designed to be universal, not custom-made for each person. But for now, the need for specialized infrastructure will keep it in select centers.
So is this really the start of a new chapter for cancer care, or just a first glimpse?
It's a bit of both. BE-CAR7 shows what's possible with precise gene editing and international teamwork. But turning this into something that helps millions, not just a handful, will need years of science, investment, and policy decisions. The potential is there. The real challenge is making sure it becomes a benefit shared worldwide.
A single teenager, cancer-free after what was once incurable. That's powerful. But the real test is whether this can happen for others around the world. That's what we'll be watching.
Thanks for joining us as we unpack the promise and the questions around BE-CAR7 and the future of cancer therapy.
Thank you for listening. This episode was powered by mynews.studio. Try now for free.